I apologise in advance if this is a chaotic talk. One reason is that I had to see a doctor at 3 o'clock in the morning. And he left at about 3:30 in the morning about a finger problem, which is causing difficulties. So we had to squeeze a lot of pus out of it, which was very painful. And I hope I can survive the lecture. Also, there are some ideas which I've only just been working on, and well, I should explain the title a little bit. The title says, "How do you do a palatial twistor theory?" which is a slight pun, because it means, how do you do it? It's also a greeting to palatial twistor theory into the sort of general framework of twistor theory. So that's the idea. So let's hope that it works. I know what I want to say, I should say, is I think I can see how to do it in the sense of what you do, but I don't know a lot of the theorems that one would need to make sure it really works. So in the case of the old construction of what's called the nonlinear graviton, we had this wonderful theorem of Godara, which told us that the construction does work, and that you get a 4-dimensional space-time out of that construction. I don't have anything like that here, so it's just what one does. And I think it's what one does, but of course that depends on the theorems to make sure that it really works. But anyway, it's that kind of a talk, but I think it's what one does, and at least it involves certain things you can manipulate and play with. Now this is just a canonical twistor theory picture. For those of you who don't know what twistor theory is, if you don't, then you're probably not a good idea to be in this talk. But the idea is basically the light rays are more fundamental than points, and you get everything being complex analytic and holomorphic and all that stuff. And that's a nice place to be, in my opinion. Now, the trouble is that light ray space is 5-dimensional, and you want a complex manifold, and you've got this extra bit, which is... Let me tell you about the idea of palatial twistor theory, which is an idea that's been around for, I don't know, 4 or 5 years, I think, as an idea, but how one actually does it has not been very clear at all. So that's what I'm going to try and say. Now, what's the point of it? The point of it is that twistor theory is meant to be a theory of physics, so that rather than talking about things in space-time and so on, you can use twistors instead. The idea being that space-time is a kind of secondary notion, and that twistor space is something more fundamental from which space-time notions can be derived. And twistor space, having all sorts of holomorphic properties, enables you to do things with complex analysis, which can be very powerful when they work. Now, the way that it's, I'll say a little bit more about this in detail, but the way that the theory has gone in terms of curved spaces is that one does things, you get Einstein's equations very nicely, but they're only half Einstein's equations in a sense. What is, you get the left-handed gravitons, if you like. They're nonlinear, satisfy their nonlinear Einstein equations, but you have things which are anti-self-dual instead of being the whole theory. That's the idea here, is to make the whole theory rather than being constricted to anti-self-dual objects. Of course, you could do self-dual instead of anti-self-dual by just going in the other direction, or you can use ambi-twistors, which is a construction which involves both at once, but you're not really, in a sense, doing twistor theory. You're doing something which is a broader framework and doesn't, in a sense, have the tie up with some of the basic constructions in twistor theory. The picture at the bottom here will explain a couple of things. Let me see if I can point to the machine. The space in the middle is twistor space down here, and the idea, this is only 5-dimensional. You're using the projective space, and if you want to consider it as a holomorphic thing, which has to be 6-dimensional. In the flat case, this is complex projective 3 space, or one may talk about the non-projective twistors, which are twistors are non-projective, so the elements of a vector space, and the vector space is 4 complex dimensional. But again, you're particularly interested in those which have a zero norm. The norm is a thing with plus plus minus minus signature, zero signature, if you like, and that means symmetrical with respect to the two sides. But the things for which that thing vanishes, that's the Twistor norm. Things in the middle. You also get sort of limits in two directions where you have self-dual on one side and anti-self-dual on the other side. I'm not going to say much about that here, but that's a useful way of looking at things. Anyway, I'll come to this in a lot more detail in a minute. But first of all, let me acquaint you with various things which, if you want to see detailed equations, you have to be familiar with the two-spinner formalism. If you're not, well, I'll just follow what I'm saying. And the equations sometimes depend on this notation quite significantly. You have the primed indices and the unprimed ones, both of which are two-dimensional, and a tensor index is a combination, a tensor product, if you like, of primed with an unprimed. Primed and unprimed are complex conjugates of each other, and the tensor indices are one of each, and so on. And the metric splits into a skew-symmetrical object, this epsilon thing, which is two-dimensional, and that sort of things which you should be familiar with, but if you're not, there you are as a rapid introduction. And here again is a rapid introduction to the Twistors. Relationship between space-time points and the Twistors. The space-time points are given by these orange things. Those are ordinary flat space Minkowski space coordinates, and the z's are Twistor coordinates, and the z's, it's useful to think of them as two-component spinners, and the incidence relation gives you the connection between the space-time and the Twistor space. And this is the incidence relation here, very simple, and the two-component spinners which constitute the Twistor are the omega and the pi. The letters are chosen deliberately because pi has to do with momentum, and you usually use a p for momentum, and this is the sort of square root of the momentum. This is coming down here. So the momentum is the pi bar, and the angular momentum, often the letter omega is used for angular momentum, and the pi and the omega together give you the angular momentum. So the massless particle in flat space can be characterized by its momentum and angular momentum, and these things have satisfied various conditions. And these come out automatically when you have this formula at the bottom relating the two spinner parts of the Twistor to the angular momentum and momentum. Now, I'm not going to say too much about that, but this is just showing you its physics, because these Twistor objects do have a very direct interpretation in terms of these very fundamental notions in physics, the momentum and the angular momentum. I should say that what I'll talk about is looking a little bit more broadly than this. This is where the flat space things are in Minkowski space. Let's say the flat, conformally flat space. I should say Twistors are basically conformal objects too. And then you have a, well, if you want to move the origin, this is moving the origin. Pi's stay the same and the omega exchange, but if you're in a conformally flat manifold, it gets more complicated, in particular in de Sitter space. Because de Sitter space seems to be a very appropriate approximation to the universe that we know, because we seem to have this exponential expansion, which is taking over now, and in the remote future will dominate the universe, and that will give us approximately de Sitter picture for space-time. And I want to talk about Einstein's equations with cosmological constant, positive cosmological constant, when I talk about Einstein's equations, and this is appropriate when one has this de Sitter, well, let's just say the flat space, the conformally flat space is not so much Minkowski space as de Sitter space. And this comes in when we talk about the infinity Twistor. I'll come to that in a minute, in a few minutes. Now, one thing that's important to what I want to say is Twistor quantization, or Twistor first quantization. Now, the Z is the Twistor, Z bar is the complex conjugate of the Twistor, it's a dual Twistor because the indices are written up and down. The down index gives you potential to the dual space to the upper index. And the natural association with quantum mechanics comes about through this quantization procedure. I could say that if you're looking at the quantized version of angular momentum, then you have these complicated relations for the generators of Minkowski space, or the inhomogeneous Lorentz group, and these are things that the P's and N's have to satisfy, commutation relations. The Twistor relations are much simpler because they are just the Z and the Z bar are not only complex conjugates, but they're canonical conjugates. So they satisfy this canonical conjugate rule. If you're talking about quantum theory, then you have this commutation rule. I shall put my H cross or H bar equal to 1 very frequently, so you won't see it often in the equations, but here it is. The Z's commute with themselves, the Z bars commute with themselves, but the Z's and the Z bars have this commutation relation. And this gives us, I should say, the helicity is essentially the norm of the Twistor. It's the polar, so you say Z Z bar plus Z bar Z. And that's a scalar quantity which, well, I'll come to that in a minute. Now, this is important if you want to talk about Twistor wave functions, and that's what this is about. Twistor wave function, you would think of in analogy with what one does normally for ordinary wave function in quantum theory, where you either use the position space or the momentum space. Here you either use the Z space or the Z bar space, and if you want to say you're using one and not the other, you would say you have function of Z which is independent of Z bar. Well, what does that mean? Well, independent of, in the holomorphic context, means that your function is holomorphic. In other words, d of your function with respect to Z bar is naught, and that tells you it's holomorphic. So independent of Z bar means it's holomorphic in Z, complex analytic. So that's what we mean by a Twistor wave function, is the function which is holomorphic in Z. And then you look at the helicity. This S operator tells you the helicity, and it's slightly shunted along from the helicity value. I mean this expression here. And if you want for a wave function for a particle, it'll be massless automatically, and you want to know what the helicity of that particle is, then that means you make it, if it has definite helicity, that means it's homogeneous at a definite degree. And homogeneity relation is given by that function down here. So if you want to talk about wave functions in Twistor theory, you're looking at holomorphic functions. And these are massless particles, so the mass is zero automatically, and I should have said that with the angular momentum. You're looking at a particle whose momentum is null, and therefore it's pointing into the future, so that's for a massless particle. Now, when you have a Twistor function, which is a function of omega and pi, if you like, you can relate that to a wave function by doing contour integrals. And these are the familiar expressions. For different helicities, you have to put lots of d by the omegas or lots of pi's. And you can see the quantization relation here, because when you take complex conjugates, the pi's become pi bars, which look like d by the omega. So these two formulae, even though they're really classical expressions here, the relationship between them you can see is from the Twistor quantization rule. So there's a kind of curious, Twistor theory kind of sits in between classical and quantum theory in a kind of strange way. You might say when you bring these commutation rules, you're doing quantum mechanics, but in a sense, you do these commutation rules are important even when you're doing classical things. So the division into quantum and classical is not quite so abrupt as you see in ordinary theory. That's a sort of philosophical point which we'll come to shortly when we talk about the palatial things. But anyway, the old Twistor functions, these are just the contour integral expressions, and you see you take a Twistor function, which is sitting in these integrals, and then you put these pi's or d by dm's, integrate them out, and you get these fields which satisfy the massless wave equations automatically by virtue of the holomorphicity of the Twistor functions, which is a very beautiful feature of the theory. And then when you come to integrals, you say, well, how do you integrate? Well, you've got to have singularities, and the story here is that you have a picture looking like this. This is the old picture I had, and I should say that in the Twistor space, if you want to know what a point is in space-time, and I think we say that very strongly, in this initial picture, here is the Twistor, and they relate to the space-time. And if you remember, these are a null twistor because the null twistor is actually a light ray. If it's not a null twistor, then you think of this as displaced somehow into a complex. But another way of thinking of that is it acquires a helicity and a complex, an angular momentum which incorporates that helicity. Now, if you kind of think of a point in space-time, then you're looking for twistors which correspond to all the null. This is a real point in space-time, all the null lines through that point, and that gives us a sphere, and this is one of the initial motivations of Twistor theory. That sphere is naturally a Riemann sphere, because it is naturally, just like this picture down here, you can think of that as the celestial sphere of a point. You see all the light rays through a point, it's a celestial sphere. That is naturally in special relativity, that is naturally a conformal sphere, and therefore it can be regarded as a complex one-dimensional space. And that is one of the important motivations behind Twistor theory right at the beginning. So you think of this as actually a Riemann sphere, which makes you try to think of this whole space in the sense of a complex space. And it turns out rather remarkably to be complex when you broaden this by introducing the helicity and making the thing somewhat non-local in a way which is both confusing and also important in what I want to say later. So, okay, so that's sort of basic Twistor theory. So the points are these Riemann spheres, and so here I've got Twistor space, and I can write a Riemann sphere either as a sphere, or I can draw it as a line, or I may draw it as a long sausage, because a long sausage looks like a line and a sphere at the same time. But if you want to think of what this topology is really like, it's a sphere, but it's a straight line in this complex projective free space. So the straight lines in the complex projective free space give you, well, complex points in Minkowski space. Now if you have one of these straight lines, then you have your Twistor function. The Twistor function has to have singularities, which are these sort of camel humps, which poke up into the top half of Twistor space. Here is the place where the twistors are null. That corresponds directly to the light rays. And here we have projected Twistor space. The top half gives you positive frequency functions, which is what you want for a wave function. But you get this if you imagine that your singularities occupy these two camel humps, and then the line up here, you extend it into what's called a forward tube. That means you make your point complex by having an imaginary part, which is past pointing. And that's the forward tube, and the function becomes positive frequency if it extends into that forward tube. That's the conventional way of doing it. In Twistor theory, it means that line moves up into the top half, and does it still work? Does your contour integral still work? Well, that is the case if you have two camel humps, and then these are where the singularities are. The thing is non-singular elsewhere, and we do a contour integral in the Riemann sphere separating the two singularity places. That was always, for a long time, a very confusing picture, and it was made clear, mostly by talks with Michael Attia and so on, where it became clear that what one's doing is sheaf cohomology. So you think of the camel humps not as two awkward singularity spots.
Roger, you've actually got that back to front, you realised.
Well, thank you very much. Of course, the picture is just as good on the way up. But you're right. Thank you. Tell me that too, because I can't see what I'm doing. This is one of the difficulties with macular degeneration. I can't read what I'm doing. And I hope you can. Okay, well, you see here is the top half of Twistor space with the camel humps removed, and the dotted place is where the holomorphic function is the holomorphic. What's left out is where it's singular. and you look at it this way, you think of that region where the homomorphic function is defined as the intersection of two regions, one of which leaves out one camel hump and the other leaves out the other. And the union of these regions is the whole top half of Twistor space. This sort of realization of what you were doing is really what changes the whole picture. So you really are talking about the whole half of Twistor space by thinking of it as being covered by these two open sets, where the intersection of the two open sets is where your analytic function is defined. And then you might think of the thing as more than two open sets, and then it's sheaf cohomology. I'm not going to go into that because either you know it or you don't, and either way there's no point in me trying to describe it. What you actually do is written down here, and then you've got to take direct limits and all sorts of things like that. And then you don't have to take direct limits because you can understand about various things in complex analysis, which means you know when you're finished, and so on. Okay, those were the linear wave equations. Now, what is rather remarkable about this is, you see here you've got a covering of your Twistor space, or top half of Twistor space, and you've got functions sitting on the overlaps. Now you can think of that if you imagine that those functions are not just sitting on the space, but they're doing something. They could give you vector fields, and those vector fields could be telling you how to slide the patches over each other, and then you get a sort of curved space. And the fact that you're doing this cohomology here is just very appropriate to say what you're... If you're working with a linearized theory, so you're not actually deforming your infinitesimal deformations, then that cohomology is exactly what you're doing. But you can do this also in a more general nonlinear case, and well, here is the nonlinear graviton construction. You do exactly the same thing, but it's the picture I just had before, that you construct a curved Twistor space where these patches are each thought of as flat Twistor spaces, and then you have these vector fields and so on. Richard Ward showed how to do this also in the context of Yang-Mills theory, where you're thinking of bundles over a Twistor space, and that's the fact that you can do either general relativity in this way or Yang-Mills theory means that it really is looking at physics in a more general way. You're not really talking just about, say, Einstein's theory or something. You're looking also at particle physics, quantum fields maybe, which connected with the other forces, not just general relativity. I'm not going to talk about this, but all I say is that the issues that are the problem here, the main thing about the talk I want to say, also applies here. So if one can solve what I call the Googly problem, which I'll come to in a second, here, that will give you a strong clue as to how to do it in the case of the Yang-Mills theory. I feel that it's not being able to do this has been a big obstruction to Twistor theory for many years, I would say, not just many years, almost half a century. I can't quite remember now how long ago it was when these constructions were done, but let me first talk about the nonlinear graviton one. This is the case of gravitation theory, and here we have our Twistor space, and we look for a line. So I'm doing a local construction in space-time. Local means you've got a line in the projective Twistor space. That's the point in space-time. And I want to be local in space-time, so I'm looking at a little neighborhood around that point. That means I wiggle this line around and make a tubular neighborhood in the projective Twistor space. So I'm going to forget about the rest of Twistor space for the moment. It's only local in the sense that I'm looking at this tubular neighborhood. But then you see you do your patching. Rather than having lots and lots of patches, I'm going to talk about two patches, because I think that most of one, at least to begin with, you don't need more than two patches, and I think that applies to what I talk about with the relational Twistor theory too. Two patches, that means you break your tubular neighborhood into two patches here, and then you imagine sliding one of them with respect to the other, and then your straight lines get broken, and then you use the Kodaira theorem to say, well, you still have your homomorphic curves. They're defined by being in the same family as the straight lines you had before, but they are now not straight, because what does straight mean anyway? But they are defined by being closed holomorphic curves. And they should be holomorphic spheres, and then Kadari tells you that you get this four-dimensional family of them, and that enables you to construct your curved Twistor space, which is very remarkable that this all works. And one wants to have...
Just about half past.
I'm sorry?
Just about half past.
Half past, thank you very much. Okay, well, this is about half the talk, I suppose. You also have to, what you might want to, this gives you, I should say, a space-time which is complex and which is anti-self-dual. Now, you may not want that, but it's what you get. If you want the thing to satisfy the Einstein equations, you have to introduce these things called the infinity twistors. Now, I'm going to do it, so it's a slightly more general construction than the one I originally had for the nonlinear graviton, which was Richard Ward's generalization to include a cosmological constant. Now, the infinity twistor does two things. It's rather remarkable that it does these two things at once. One of them is to give you a metric. Up to this point, you've just had a conformal structure, but the infinity twistor tells you what the metric is. And when you put the lambda in, that's a cosmological constant, so that would give you the de Sitter metric. Now, it also gives you the Einstein equations, and it gives you the two things at once. So it's rather curious that the twistor theory, without the infinity twistor, is a conformal structure, and you don't have a metric. But as soon as you put the metric in, along come the Einstein's equations with it. Now that's very curious, and to what extent it's even true needs to be, well, needs some proper theorems, but it does seem to be the case that that's what you get. Now these infinity twistors are skew objects. They're conjugates of each other. They are also duals of each other, and they correspond to two forms. So this infinity twistor is a two-form Z, and they're degenerate if lambda equals 0, but it's a symplectic structure, a genuine non-degenerate symplectic structure, if you have a cosmological constant. I think it's important that you do have a cosmological constant. Well, the reason which I'll hint at later. Okay, now, here's the problem. The googly problem, and those of you who come from the former British Empire know all about googlies because that's a cricketing term. It's a ball which is bowled as though it spins left-handed, but it actually spins right-handed. So it's a very appropriate name because the left-handed construct, see, in the normal twistor conventions, everything I've been saying gives you the, well, not everything, everything nonlinear I've been saying gives the left-handed construction. What you need is to do the right-handed one within the framework of the left-handed construction. You could go and do ambitwistors, which means you just take both constructions at once. But I want to follow the sort of quantization rules and the wave functions and all that sort of thing, which seems to me indicating that it's probing something about the nature of quantum physics. So that's really why I tend to steer clear of ambitwistors and things, although I'm sure they have a role to play in this. Okay, now the googly problem is that, okay, we automatically get these anti-self-dual things. I can't see what I've written, but I hope you can read it. But what we want is a formalism which enables you to do both at once. And the idea, which came about partly from a conversation I had with Michael Thiel, where I was saying I want to have a construction where you patch things together, but you don't have the spaces. Because as soon as you have the spaces to patch together, you're driven into this anti-self-dual thing. So to get away from anti-self-dual, I had all sorts of other ideas of how to do googlies. I'm going to forget all of them. They tended to imply going out to infinity, and infinity is rather simpler than locally. And that enables you to do things that are not easy to do locally. But it seemed to me that we want to do something which is much more local. When I say local, it's not really local in the sense that it's at a point, but it's sort of here, rather than having to go out to infinity. So, in that sense, it's local. Now, this is just, yeah. So what is Twistor? What is palatial Twistor theory? I had this conversation with Michael, you see, and I said, how do you patch things together when you just have this sort of sheaf of functions or something? And he said, well, that won't work, because once you have the sheaf of functions, you've got the prime ideals and you've got the space back there. I sort of knew that, but I wasn't facing up to it. And then he paused for a minute and said, well, that won't work if you have a non-commutative algebra. And I thought, wow, yes, we have this algebra which sits there in Twistor theory, which is waiting to be used. So this is really the key. You use this non-commutative Twistor algebra, try to patch things together, but you're using the algebras instead of the spaces. And that algebra, you think of it as sort of sitting above the spaces, but spaces aren't really there. Then, because the algebra being non-commutative, you can't reconstruct the points. Now, in a certain sense you can, which is rather useful. You see, if you are talking about the null twistors, which represent by light rays, you have actually a right light ray space. So that space is really there. You see, there's a lot of problem about defining open sets and all that sort of stuff. And I get completely tied up in knots trying to understand what you mean by patching together with open sets and all that with algebras, when none of these ideas sort of make sense. And I won't go into why they don't make sense. At least, maybe they do if you do it right. But it doesn't seem to me that I've at least seen the right way to do that. However, if you can think of all this as being close to the space of null twistors, so you're thinking of the light ray space is sitting there, and then the patchings are to do with that. And then you think of extending in some sense into this complex region. Now you may do this in different ways. So you've got the light ray space, which is this sort of central region, and twistor space, you've got the two halves. Now you're sort of trying to poke your way down into the two halves, and you may have ambiguities to how to do this, but that ambiguity, each possible way of doing it is sort of what you would look for a patching. I'll try and be a little bit more explicit about that. But the idea is you do think of two patches like this, could be two, you probably just two you get away with, at least initially, and you try to patch the algebras. So that's what I'm trying to do. Now, how do you do it? And what on earth are we talking about? Well, that's one of the problems. One of the keys to this, I think, has been to think in terms of geometric quantization. Now, Nick Woodhouse is a great expert on this, and he's written a very fine book on the subject, which is very useful to have. But the basic idea is that you've got a symplectic manifold, and you want to turn this into a quantum theory. Now, the first thing you do is to construct over that symplectic manifold a circle bundle, and that circle bundle, you construct connections in that circle bundle. And those connections satisfy canonical quantization rules and so on. So you get a sort of quantum theory which comes out of this. Or you get a pre-quantum theory and then you try to make that into a proper quantum theory. Now these ideas are very natural in this context because you have a symplectic manifold. You see the null twistors, and let's think of them as having a scale too. I'm not talking about the projective. You have the top half and the bottom half of twistor space, projective ones, and the top half is called PT, projective PT plus, projective positive twistors, PT minus down here, and PN is the one in the middle. N is the null twistors, the P says your projective null twistors. If you're looking at the non-projective ones, then you've got the space N. Now the space N is 5-dimensional, it's 7-dimensional. The projective one is 5-dimensional, that's the light ray space, but the non-projective one is 7-dimensional. Now what is the two extra dimensions? Well, one of them is the momentum, so that gives you a scaling to the light rays. The other is a phase. So you've got a little flag plane, which tells you, and you rotate that flag plane around, and that gives you the e to the I theta part, that's the phase part. Now you see, the momentum part, if you include that, you have something which naturally has a symplectic structure. And this is true whether you're looking at flat, conformally curved, or what. This is just natural for the null rays. The null geodesics in a space-time doesn't have to be four-dimensional space-time, it can be any other dimensions. And you make the light ray space and you include the scaling, which is the momentum part, so you've got another number, and that is naturally a symplectic manifold. Now, you see, you construct a circle bundle over it. Now, the nice thing here is that circle bundle is already there. It is the phase of the twistor. So that seems to be rather nice. It fits in naturally with this twistor quantization procedure. This is the phases when you multiply the pi spinner. See, the momentum is pi times pi bar. The phase is the theta here. It gets washed out when you do this. And then you construct your normal symplectic manifold using the momentum here. So you have a symplectic manifold even in the curved space. So the whole thing is there. It doesn't have anything to do with the space being conformally flat. That's all there. Okay, so we can do some ideas of this nature. Actually, I can see there's a slight digression in what I want to say in my next transparency, but let me do that anyway because it's sort of important to what we're doing here. These are the twistor quantization rules, which are what I'm going to be using in this construction. It's still classical theory, so I'm trying to construct a classical curved manifold. It's a curved and conformal manifold, so we know what when the light rays intersect. You have a conformal structure. The light cone is a conformal thing in any dimensions. Now, what about these commutations? I just write them down here because I'm still thinking about it. You see, this isn't doing quantum gravity. It's not even trying to do quantum gravity because even though I've got an h bar here, there is no length. So there is no role for the Planck length in the construction. When you're just stuck with these commutators. Although these are complex quantum mechanical things. I mentioned there's this kind of funny relation twistor theory has to quantization procedure. It does things which look like quantization, but you're still doing classical theory. And that's a bit strange. But if you want to do quantum gravity, then you would bring in these other commutators. Now these commutators are between z's and z's, and the infinity twistor sits here. Now this does bring in a length, and therefore the Planck length, and therefore that has a chance of being something to do with quantum theory. See, when some people ask me, say, why on earth are you doing this? Because it's all very complicated, and what's it for? Well, the reason is I'm trying to bring twistor theory into a physical theory which includes right-handed and left-handed things at the same time. If you're going to talk about classical space-times, you need to do this. And it brings in this sort of quantum ideas. However, it's not quantum space-time as yet. It could be if you bring in these other commutators. Now, I'm not going to do that here. I don't know how to do it. But you have your eye on this all the time. So the fact that these other commutators are there leads you into some notions about quantum gravity. That's an exciting possibility, but you have to get this stuff straight first. The palatial stuff I'm doing here, I'm not worrying about those other commutators just yet. Okay, let's try and do the palatial stuff. Now, I'm afraid I made these transparencies yesterday, or this morning, actually, and they're probably a bit of a mess, but I shall try and tell you what I'm trying to do rather than try to read them. You can try and read them. Now, I'm going to borrow some ideas from geometric quantization, which leads me to thinking about geometric quantization. You look for the spin bundle, well, you've got this circle bundle over the symplectic space, and then looking for connections in that bundle. And these connections satisfy non-commutative commutation rules. And I want to make those look like the commutation rules of the twistor theory. So that's the idea. And the canonical case is the following. I think of these operators d by dw. W is z bar, but I'm...
Quarter two is about 42.
Sorry?
It's about quarter two.
Quarter two. Okay, well I shall have to hurry, I think. These z bars, you make them independent complex things. So this is a useful concept. So the w's are really z bars in disguise, but they are independent of the z's. You make them z bars at the limit when you want to make things real. But for the complex things, you have them independent. And then here I have the sort of basic commutation rule, which is, when I say canonical commutation, I'm going to say I've got two operators, and I say that the lefts commute with the lefts, the right commute with the rights, but the left and the rights have this commutation rule. Okay. Now, this is the simple case, but you see, if I imagine these acting on a space which is holomorphic in Z, then the d by dw's disappear and you're left with z's. And so here you have the commutation rule between d by dz and z. But it's more general than that because I needn't be looking at the space of holomorphic functions. I think of that as a sort of ket space. See, the philosophy here, going back to what I was saying here, is that what's incompatible with the... See, I can think of this algebra as acting on some space of holomorphic twistors. So it's a curved twistor space or something like that. These are the z's, which are holomorphic. And those operators are sort of z's and d by dz acting on that space. But then I think of that algebra as a thing on its own. And you throw away the realization in terms of z's. So we call that the ket space in the sense of Dirac. You've got your ket space when you're over there on the right-hand side and bars on the left-hand side. And the ket space, if you stuck to one ket space, you wouldn't get this construction. So you have a construction which you have a particular ket space which works on this side and a different one on that side. And this over here is a set of holomorphic functions, and over here is another set of different holomorphic functions where the algebras go over from one to the other, but the ket spaces don't. So that's the picture that you have to have. So this is what I'm trying to do here. Now, it's probably a bit of a mess, and I can't read it myself, so probably you can't. But this is the canonical case here. You want to make that more general, and you can do that by adding in some functions here, and these things have to satisfy. Well, it's basically having to do with your two form, which is the phi here, and you think of that as the d of a one form. And that one form is the thing which makes your connection into a more general one. You see, you add that one form into the connection, and that makes it not commute with the other things. So if you didn't have that, you wouldn't have non-quantitative geometry. But you have to take a one form, whose d is this two form, and that one form gives you the algebra that you're interested in. This is just how I was doing it before. And it's a bit of a mess because you want to do anything explicitly. Well, let me see, this is just a geometric picture of what we're doing. You think of your z's and w's and you shove them around. I'm not going to talk about that much because I haven't got time. But let me talk about the better thing that I'm trying to do. It's a great mess just to think of these f's and g's. So I know this is a general case, but if you try and find your holomorphic space out of them, you have to solve implicit equations, and I have no idea. People who are good at that and others will do it, but I find it terrible. So it's much better to use generating function. And this is the key thing. You have a generating function which is just in gamma. And gamma, here in this bracket here, you see, gamma is a function of the z's. I've used two coordinate systems, if you like, or think of them as two twistor spaces. There's the z and w, and the curly z and the curly w. These are the two different spaces. And I want to match their the algebras, but they are thinking of different spaces, if you like. At least the holomorphic spaces are different. And to get your z's, your transformations, you simply differentiate. See, it's a mixture of the z's from one system and the w's from the other system. And then you partially differentiate this function with respect to the z's to get the curly z's and with respect to w's to get the curly w's. And it's all very explicit and very beautiful. I've always thought of these things as very nice. Now, when I last thought about this, I realized I had made a mistake because I thought that this function, gamma, had to be homogeneous to degree 1, 1. That doesn't work. It has to be a homogeneous degree 2 altogether. So what I mean is that thinking of the z's and w's together is homogeneous degree 2. And then that means that you have an equation like this, w dot dww plus z dot dwz acting on it gives you 2 times gamma. And this seems to work. So that was an important step. Now, how about the Einstein equations? Now, I've been struggling with this recently for a long time. I thought we'd try to preserve these forms. So these these two forms, I'm not doing quantum gravity here, I'm just thinking of these two forms classically. Now, these two forms, you might think you have to preserve. You see, when you did the nonlinear graviton construction, or particularly Richard Ward's version of the cosmological constant, you take that two form and you preserve it from one side to the other, and that gives you the Einstein equations. So the Einstein equations are given by preserving that form. Now in this case, I realized after a long time that that gives you an inconsistency. At least it doesn't give you anything important that's new. So what you have to have as your two form is the sum of these two things, z's and the w parts together. Now, I'm going to use a notation here. I think this is probably here. I'll find my piece of paper. Yes. Do I have a few minutes?
Sure.
I'm going to use this notation. You see, here is the infinity twistor. It's really rather handy. I've used wiggly lines for the curly W and Z system. I use straight lines. You see, when I use alphas and betas, you know whether these alphas belong to the same space as these ones. It's confusing. I should use a different alphabet here as here. And I do that by using my notation. Now look, maybe people won't understand the word I'm saying here. I'll leave this here, and I'll try and show you how you do some calculations. And I think this gives us, you see, this expression here stands for, this is the second derivative, this stands the second derivative of gamma with respect to the w's, the wiggly coordinates. And this is the infinity twistor stuck in it. And what this has to preserve is this thing, but not completely. It gives you alpha times this. This is the infinity twistor. There's an alpha. It doesn't give you this automatically because the thing you preserve has to be the sum of those two bits. And that was what I didn't realize at first. This is the key thing. Now, you also have this thing, which is this again is the infinity twistor, but that's in the other system. And then you have to you also have to have this bit. So these equations look a bit complicated if you write them all out. But if I put these pictures, you see, then I can understand what I'm doing. Whether you can understand what I'm doing is another matter, but I'm just showing you what I do. And these are the equations you have to satisfy. Now this seems to me like an awful mess though. You've got these rows and things and so on. It still looks like an awful mess because all these expressions stand for second derivatives with respect to the gamma. And you've got all these things, and you want to make sure that all these equations are satisfied, and one of the alphas and betas. But you can do some simple. Well, first of all, let me give you something which relation which automatically, to make this thing work at all, you find you need this relationship, which is when you get used to these things, it's much easier to calculate with them than to write them down. It's really much easier. I can perhaps show you how to do the simple thing. Let me show you how to show that alpha equals, let's see, beta equals rho. We can do that, I think. You see, we can do that here. Let me do it. I'm going to consider this expression. And then sort of expand it out in two ways. So it's good. And you expand it out in two ways. One is you can see rho times using that relation to green one at the bottom. And you have to know that this is equal to lambda, what is it? Minus lambda over 6. Cosmological constant really is useful here. These things become singular otherwise. It might be easier to work with them, but you don't see what you're doing. So this is that, and it's also, and that's equal to, so lambda over minus lambda over 6 or something times, and then you do the whole thing the other way around, and you get that's equal to minus lambda over 6. Sorry, there's times a rho, yes, times a beta. So it's rho equals beta. And then we do a similar thing with things like this. I've got it right. Let me not go through it. It's very simple. You see all these things. I was going to write it out in ordinary notation. That is sort of symmetrical by flipping it over, and the wiggles go to the unwiggles. So it's I think it's clear. That's what it is. So I can expand that out in two ways, and one gives us, that's right, gives you minus lambda over 6 again, times this, times alpha, and then the other one gives you this times lambda minus lambda over 6. The same thing, times sigma, so alpha equals sigma. So we know all that from these calculations. And then you say, how do you solve all these equations? If you're going to, it's still a bit of a mess, all this. If you want to try and solve the equations, well, the idea is to try and do it with a generating function. And what you'd like to have is this form, well, this is the dz wedge dz that we have. But you've got to add this to the dw one. Now, the thing is, if you've got z's, you don't have the w's, because the w's are, and this is the true form, so you could think of getting this with a generating function. That's the idea, but this is the wrong w, because what you got with your generating function, I don't know these w's. I know this one with the curly w. So you look at the equation, where have I put it? Here, I guess it is. At the top then, I think. And you need to have the curly version instead. So you instead have alpha to the minus 1. Alpha to the minus 1 times the curly w. The curly w. And then you can think of the symplectic form as in the space in which gamma is defined, and so you can write down a generating function for solving these equations. The only thing is you've got alpha. But then you can see that there will be an equation for alpha. So for this to work, you see you have an equation for alpha. And I think that what you do then is use the generating function. You have only one equation to solve, because it's the one for alpha. I haven't gone through this yet, because I haven't finished this stuff, and I told you I was in the middle of it. But this idea is that you want to make sure that you can find your generating function gamma, which gives you the Einstein equations in your patching automatically. And you do that by having a second order generating function, which is what I'm saying here. You put the alpha in, and then it does work. You get a generating function, but you have an equation for alpha. Only one equation for alpha, and that gives you everything else. But wait, it's sort of It's work in progress, and I haven't done that last bit. Whether that lends me to something horrendous or not, I don't know. But it does seem to me that there's a genuine route here for finding gammas which give you automatically what you want, so that the patching gives you the Einstein equations. Now, it's still not going to be, I mean, the old construction was a mess. If you want to solve things explicitly, I'm not sure whether I've written the right thing down on that transparency. Oh dear. Let me just tell you. What's a point in this space? Well, you see the analog of the Riemann spheres and the homomorphic thing in the old construction, the nonlinear graviton construction. What's the analog of it here? Well, you've got to find something in the algebra which corresponds to a point in space-time. And what that is, certainly it's true one way around, what it is a subalgebra which is completely commutative and which is two-dimensional and is self-conjugate. And you can see when you've got a point, that's exactly what you have. Now, is that a sufficient condition to characterize the points in the relational construction? I think it's a good chance to be true. I haven't proved anything, and even if it's the right thing to do, I don't know what the Kodara theorem is, which tells you you're going to have a four-parameter family of these things. But that seems to be what you do. That, of course, is difficult to do, even when you've got the... See, let me just say, the initial part of the construction is to do the patching. Now, if what I'm saying here is right, it's not so hard to do. If you want to construct a space-time which is just an ordinary space-time, that's easy. You just use a generating function in the way I said. If you want to satisfy Einstein equations, you've got to use the second-order generating function, which uses the alphas. And that, I have to see if that works. But let's suppose it does. Then how do you get your space-time out of which satisfies the Einstein equations? Well, that's the hardest altogether, probably. You've got your algebra, but you've got to search within that algebra for these completely commutative two-dimensional subspaces which are self-conjugate. And that seems to represent the points. It's bad enough for the old nonlinear graviton construction. It's probably horrendous in practice here, but that isn't the point of the construction. The point is, do you actually have a way of representing, first of all, classical space-times in Einstein's theory, and then by going further and trying to do this with the other commutation rules, which I haven't been trying to do, might that give you some idea of quantum gravity theory? Well, that's something for the future, and I'm just giving you the current situation. Thank you very much.
So what do you really want points in this?
Yes.
So do you
What you really do for the real construction and for the Einstein equations? Yes. So this is classical.
So the conditional the bigger algebra is
Yeah, these subalgebras of the non-commutative. Yes, these subalgebras which are two-dimensional. And you can see when you've got a point, what you want. It's really that the pies can be something and you've got a two-dimensional algebra. So that's what you have. But whether that's a sufficient characterization of a point is what I don't know. I think it likely is. It's quite a strong condition. But that's still classical general relativity. And it's using quantum ideas, you're using ideas of Ket spaces. From Dirac, you see, you're looking at how you represent these algebras in terms of functions on a homomorphic space. But still, it's classical general relativity.
questions? Yeah, you have.
Well, you can write down the Hamiltonians to form these spaces, I guess. So
Yes.
that's corresponding to linear solutions to the Einstein equations.
Yeah.
And so I was just trying to check that they actually do. Or maybe I should talk to you after.
Yes.
Sorry, I haven't finished the
It
calculation.
sounds like an interesting discussion.
But I mean, the Hamiltonians that do this in linear theory, correct this.
That would be very nice to tie that in with that.
Yeah.
Yes, indeed, of course. Yeah, no, I very much like to see.
But do you see a role for a -6 function? This is all plus 2
Um,
plus minus.
Well, that's a good question too.
So I only see a role for a +2.
It must be there,
Mm.
but you see, it's
Maybe
tied
not
in with the
both.
fact that I need the total homogeneity to be 2,
Mm.
which is sort of curious, but then it mixes them together. But I guess if you're going over to one space, then it'll make that homogeneous -6 correspond to a +2 function. Yeah, but that needs looking into. Yes, yes, I hadn't thought of it looking at it from that perspective. But yes, that's right, appreciate it. One needs to do that. So there are a lot of things to tie it up with, and I think what you're saying about the Hamiltonians is probably the first thing to look at. Let me know.
Okay,
Yes.
I'll do it later.
Yeah, great, yeah.
Any other questions, comments? Well, if not, let's thank you all for again.